Greetings to all ICMC participants. I am Robin and my partner Martha from Bandung Institute of Technology. Now, we are going to give you a brief presentation about risk quantification and volatility prediction for traditional cryptocurrencies and stablecoin using a superfactor regression approach. In this presentation, there will be 5 main parts, which are introduction, data, methodology, empirical result, and conclusion. Cryptocurrency markets are highly volatile and full of uncertainty. Consequently, participants in this market are exposed to high risk that can potentially make them gain extreme losses. Therefore, cryptocurrency risk is important to be quantified. In this study, risk quantification is done on some return series that span during normal and pandemic periods. In particular, we use the return of traditional and stable cryptocurrencies. For comparison, gold return is also considered. Return series is expressed as a collection of random variables denoting return at discrete time points with a certain conditional distribution function. To quantify its risk, we use a tool named value at risk or VAR. The value at risk consists of volatility of the return that has the property of volatility clustering. To capture these volatility properties, we use a heteroscedastic model, namely general autoregressive conditional heteroscedasticity or GARCH. In addition, the return is commonly heavy-tailed and even skewed, which means that the choice of distribution is crucial. To avoid misspecification in choosing this distribution, the GARCH model is extended using SVR that doesn't need a distribution assumption. The data that are used in this research are Bitcoin, Ethereum, Tether, and Gold close price, and those data are obtained from Yahoo Finance. We also divided the data into 2 periods, which is normal and pandemic periods. The daily financial return are converted from the corresponding close price, PT, using continuous compounding transformation as written in equation 1. This slide shows the visualization of assets close price and return. The yellow line acts as an indicator for the start of pandemic period. The skewness and kurtosis for all assets shows that the assets don't have a normal distribution. Having high kurtosis indicates that the assets have heavy tail distribution. According to Chang 2018, cryptocurrencies have specific statistic properties, such as having heavy tail distribution, conditional heteroscedasticity, and autocorrelation. To ensure these properties, we use Jarque-Bera, the Jungbox, and ArchLM test. The null hypothesis for Jarque-Bera test is the skewness being 0 and the excess kurtosis being 0. The null hypothesis for the Jungbox test is that the data are independently distributed. The null hypothesis for Arch test is that the conditional heteroscedasticity up to like k cannot be detected. For all the statistical tests, the null hypothesis is rejected under alpha 1%. That means the data can be used for the next step. The figure below shows the model flowchart for this research. To test the volatility clustering effect, we employ GARCH, which is the most frequently used model. A GARCH model is a statistical model that captures the conditional heteroscedasticity. One of the objectives in this research is to find the best GARCH model for its assets before the GARCH model is extended by SVR. The GARCH model is represented in equation 2 until 4. Mu and sigma is the conditional mean and conditional variance, respectively. In this research, the innovation, ZT, is assumed to have skewed student T distribution. The necessary and sufficient condition for the second-order stationary of GARCH model is that the sum of eta and beta coefficients must be less than 1. The conditional mean below equation 2 is modeled by autoregressive one-day lag or AR1. In order to find the best GARCH model for its assets, we use AIC and BIC as a matrix to evaluate the model performance. GARCH model with the smallest AIC and BIC for each pair combination are chosen to be used in the next step. Now, we continue to the SVR-based GARCH method in terms of estimating the GARCH parameters. The support vector machine, or SVM, is a machine learning algorithm based on the statistical learning theory developed by Vapnik. For linear and nonlinear regression, SVM is called support vector regression, or SVR. The main goal for SVR is to find the best regression function to approximate the output variables. One of the advantages using SVR is that the algorithm can approximate nonlinear relation of the input vector by a linear regression. SVR maps the input vector to a feature space, so the nonlinear relation of the input vector can be approximated by a linear regression in the feature space, where W and scalar B are the regression parameter of SVR. The function P is the nonlinear mapping function which projects the input vector into a feature space. The SVR uses penalty parameter named C, in which the sample with a prediction error lower than epsilon in absolute terms are not penalized, and those samples with a prediction error greater than epsilon are linearly penalized. Here are the SVR quadratic optimization problem, leading to minimization of the risk function. The quadratic optimization problem can be solved by introducing constraints using Lagrange multipliers. Using Karuskal-Tucker condition, or KKT, the problem above can be solved in the dual space by substituting KKT into the primal equation. We arrive at the problem of maximization of dual variable Lagrangian. The main problem when SVR maps the vector into higher dimension is if the multiplication of P function has a very high dimension, it causes high computational power. This problem, often called curse of dimensionality. To overcome this problem, a kernel function is introduced. This function has the same value as the multiplication of P function, but has the same dimension as the input space. So the P function is no longer needed. In this study, we use 3 different kernels that are linear, polynomial, and radial basis function.
Next, we move to the SVR-based GARCH. For the SVR-based GARCH, the input vectors are square residuals and volatility from the previous days. The conditional mean is modeled by an autoregressive model written in equation 12, where f is the decision function estimated by SVR. Because the volatility is not directly observable, so it is necessary to use proximity. As in Chen 2010, the volatility proximity is written as below. In equation 13, each function is the decision function estimated by SVR. This framework is obtained from Becerra 2016. After maximizing the dual Lagrange equation in the SVR problem, we get the delta values to be used in the SVM regression equation. The next step is to convert the SVM regression equation into SVM decision function to obtain the GARCH parameters, where W is a vector that contains GARCH parameters. So in this slide and the next one slide show how the linear kernel transformation. To evaluate the SVR model, we use mean absolute error and root mean square error as the evaluation metrics, where tilde volatility is the observed data and the head volatility is the predicted data. We also use Pearson correlation to see dependency between the asset and observe whether the asset serves as a diversifier, hedge, or even safe haven for each other. When an asset that is positively but not perfectly correlated with another asset or portfolio on average, this asset is defined as a diversifier. On the other hand, an asset that is uncorrelated or negatively correlated with another asset or portfolio on average, this asset is defined as hedge. For an asset that is uncorrelated or negatively correlated with another asset or portfolio in times of market stress or turmoil, such as COVID-19 pandemic period, is defined as a safe haven. After we use SVR-based GARCH to forecast asset volatility, the next step is to quantify the risk using value at risk. Value at risk can be interpreted as the worst loss of an asset over a period of time in a certain level of confidence. In this study, we used the one day ahead method to calculate the value at risk for every asset. Let G inverse correspond to the desired quantile of the innovation distribution density function, and hat sigma and hat mu is the predicted volatility and mean respectively. According to Look 2019, the estimated innovation can be obtained as below. In the table 5, show the best gauge model that has the smallest AIC and BIC value for each asset in the normal and also the pandemic period. For the next step, those gauge models are used in the SPR-based gauge method. In terms of finding the best parameter for SPR, which is C, gamma, epsilon, kernel, and also the degree, Bayesian optimization with mean absolute error or as the validation metric is used. Bayesian optimization builds a probability model of the objective function, or in this case, the function to compute the MSA, and use it to select a hyperparameter to evaluate the true objective function. The value range for every parameter is written as below. In this table and the next table show the best SPR parameters and also the best SPR-based gauge parameter as the result of the Bayesian optimization method. And this table shows the mean absolute error and root mean square error value for every asset in the normal and pandemic period. Using the one day ahead method, we predict the amount of maximum loss or negative return with 10%, 5%, and also 1% confidence level. This table shows the result of value at risk calculation in the normal and pandemic period. As we can see from the four assets, mainly Ethereum has the highest risk and Tether mainly has the lowest risk compared to another asset. The value at risk result can help the investor to set up a proper risk management strategy in terms of surviving the maximum loss at the worst day. As we can see at the heat map, Tether acts as weak hat for Bitcoin and Ethereum, but has nearly zero correlation with gold. In the pandemic period, Tether turns into a safe haven for Bitcoin and Ethereum. And gold is also considered as a diversifier for Bitcoin and Ethereum in both periods. And then we jump to the conclusion. So, from the value at risk calculation in the normal and pandemic period, we can see that from the four assets, mainly Ethereum has the highest risk, and Tether mainly has the lowest risk compared to another asset. In the normal period, we confirm Tether's capability as a weak hedging asset for Bitcoin and Ethereum. In the crisis period or pandemic situation, Tether turns into a safe haven for Bitcoin and Ethereum. On the other hand, gold has lower value at risk but only serves as a diversifier for Bitcoin and Ethereum, both for the normal and also pandemic period. So that's all from our presentation. Thank you for your attention.